By forcing crystal structures to compete, scientists uncovered a new way to make magnetism twist. Florida State University scientists have developed a new crystalline material whose magnetic behavior differs sharply from that of conventional magnets, opening potential paths toward advances in data storage and quantum technology. Reporting their results in the Journal of the American Chemical Society, the team demonstrated that combining two chemically similar materials with distinct crystal structures can produce an entirely new structure. This newly formed material displays magnetic properties unlike those seen in either of the original compounds. Magnetism arises because atoms behave like tiny magnets, a result of a property called atomic spin. Each spin can be pictured as a small arrow that marks the direction of an atom's magnetic field. In ordinary magnetic materials, large numbers of these spins line up in an orderly way, either pointing in the same direction or in opposing patterns. This collective alignment gives rise to the familiar magnetism used in devices such as computers and smartphones. The Florida State researchers found that their method leads to far more intricate spin arrangements. Rather than lining up uniformly, the atomic spins organize into repeating swirling patterns. These structures, known as spin textures, strongly influence how the material behaves magnetically and set it apart from traditional magnets. How it works to create the material: the team blended two compounds that are close in chemical makeup but differ in the symmetry of their crystal structures. When these mismatched structures meet, they generate what scientists call frustration, meaning that neither structure is fully stable at the boundary between the two compositions. This instability plays a key role in producing the unusual magnetic patterns observed in the new crystal. We thought that maybe this structural frustration would translate into magnetic frustration, said co-author Michael Shatruk, a professor in the FSU Department of Chemistry and Biochemistry. If the structures are in competition, maybe that will cause the spins to twist. Let's find some structures that are chemically very close but have different symmetries. They combined a compound of manganese, cobalt and germanium with a compound of manganese, cobalt, and arsenic. Germanium and arsenic are neighbors in the periodic table. After the mixture solidified into crystals, the research team examined the product and found the distinctive cycloidal spin textures that they were seeking. Such swirls of spins are known as skyrmion-like spin textures, and the search for more ways to find and manipulate skyrmion hosting materials is a cutting-edge research area within chemistry and physics. To determine this skyrmion-like magnetic structure, the team collected single crystal neutron diffraction data on the TOPAZ instrument at the Spallation Neutron Source, a U.S. Department of Energy Office of Science user facility at Oak Ridge National Laboratory. Why it matters: this research could be used to develop hard drives with greater information density or improve electron transport efficiency. Because using magnets to move skyrmions takes little energy, incorporating materials with these magnetic patterns into electronic devices could reduce power consumption. In massive supercomputers with thousands of processors, these lower power loads can lead to huge savings in electrical and cooling costs. The research could also help point scientists and engineers toward promising materials that can help develop fault-tolerant quantum computing, which can protect fragile quantum information and operate reliably despite errors and noise, the holy grail of quantum information processing. Why it matters: this research could be used to develop hard drives with greater information density or improve electron transport efficiency. Because using magnets to move skyrmions takes little energy, incorporating materials with these magnetic patterns into electronic devices could reduce power consumption. In massive supercomputers with thousands of processors, these lower power loads can lead to huge savings in electrical and cooling costs. The research could also help point scientists and engineers toward promising materials that can help develop fault-tolerant quantum computing, which can protect fragile quantum information and operate reliably despite errors and noise, the holy grail of quantum information processing. That understanding of the fundamental science at work could point to promising directions for future research. The idea is to be able to predict where these complex spin textures will appear, said co-author Ian Campbell, a graduate student in Shatruk's lab. Traditionally, physicists will hunt for known materials that already exhibit the symmetry they're seeking and measure their properties. But that limits the range of possibilities. We're trying to develop a predictive ability to say, if we add these two things together, we'll form a completely new material with these desired properties. A benefit of that approach is the ability to expand the ingredient list for making materials that contain skyrmion-like spin textures, allowing for cheaper, easier to grow crystals and a more robust supply chain for future technologies that might benefit from such materials.